Hello, good morning, friends. Today in class number 4, I am going to explain examples of holonomic constraints. We have defined constraints and we have discussed so many examples. Okay, we will discuss one by one. Say for example here, a particle is moving or allowed to move on the circumference of a circle. Example 1. A particle moving on the circumference of a circle of a circle. Fine. Let me take this circle. This is circle with center as O. Let AB is radius, say R, and say P is some particle moving on the circumference of a circle, P of xy. To describe the motion of a particle on a circumference of a circle, normally we call it as a circular motion. What we'll do is we'll select a coordinate system. This is x-axis, this is y-axis. We need two coordinates, x and y, in case of say Cartesian coordinate. R is, O is the center of this, A is the radius, and P is the position of particle at any given instant of time, and R is known as the position vector relative to the center of a circle here. P is the position. To describe the motion, we want to find out an equation. Here, the constraint in this example is the particle is allowed to move only on the circumference of a circle. Well, here the circumference of a circle is given and R is its radius, and this position vectors at a given instant of time t makes an angle theta with x-axis. So either we can analyze this problem and we are going to say this is an example of non-means example of holonomic constraint. Fine. So P of xy is the position at any given instant of time t. Well, we need two coordinates here in terms of Cartesian coordinate. Now, the selection of coordinates is an important aspect here. Either I can go for a Cartesian coordinate or for a polar coordinate. So, we can write this as x square plus y square is equal to, say, A the radius, A square. If I write this x square plus y square is equal to, say, R square, the position vector, which is equal to A square. Now, what is the constraint here? This particle is at a distance A from the center of a circle. The particle is allowed to move on this specified or in a specified path. A is the radius of the circle, and particle is moved on the circumference of a circle with this distance a, the constant. Here the constraint is particle is allowed to move with a constant distance from the center, that is a, the radius. Now we have the coordinates x and y, or r and theta. R and theta. R is the position vector. In terms of polar coordinates, we can say r and theta are the coordinates. Either x and y are the coordinates, or r and theta are the coordinates. We have selected this x and y. We have written its equation. So this becomes r square, which is equal to a square. A is the radius and r is the position vector with reference to the center of a coordinate system. Now the coordinate system is imaginary fixed at this point. We imagine the origin of the coordinate system, that is x and y, is fixed to the center. We never draw it, but to analyze this problem I have shown it here. We draw the circle directly, we write the equation. We assume that there is a coordinate system and which is fixed at the origin of the center of a circle here. Well, this x square plus y square is equal to a square, r square is equal to a, or I can write r is equal to a, or I can write r minus a is equal to 0. This radius is equal to, say, the position vector. That means this is constant, and that is the constraint here in this example. Now we require two coordinates in terms of polar r and theta, in terms of Cartesian coordinate x and y. Look at this example from this polar coordinates r and theta. R and theta. Since this coordinate remains same, we have shown it is equal to r is equal to a, or r minus a is equal to 0. That means out of the two coordinates we have eliminated one coordinate, and what is remaining with us is the only coordinate. Now I can write this as independent coordinate is equal to theta. Q1 is the independent coordinate and its only coordinate which we require to describe the position of a particle here. And here this single coordinate is enough to describe the position of a particle. Fine. And this number of coordinates, independent coordinates, are equal to the degrees of freedom. So Q1 is equal to theta, which is equal to 1, the degrees of freedom. This is one example. We'll pass on to another example, that is example number 2. So we all know that when a particle is free to move, or whenever a particle is moving freely in a free space, for that particle we need three coordinates x, y and z, or r, theta and phi. And the degree of freedom for a moving particle which is moving in a free space is, say, 3. Now, such a freely moving particle, we make that particle to move on the surface of a sphere. Particle is forced to move on the surface of a sphere. So this is a sphere and this is its center, a spherical body, and particle is allowed to move on the surface of this sphere. When a particle is constrained to move, force to move on the surface of a sphere, there exists a relation between the motion of a body or a motion of a particle on the surface of a sphere and the sphere. Say, to describe its motion, say this is a spherical body, we have three coordinates, say x, say y, and say z. So O is the origin. Say the particle is somewhere here, P of x, comma y, comma z, and it makes an angle theta. Now, looking at this, so it depends upon you, depends upon the reader who reads the subject. Say, how to select the coordinates, what or which coordinate set is to be selected. So here, in this example, instead of selecting what is called as Cartesian coordinate, I will go with polar coordinate. Later on, using say polar coordinate here in this case, that is r, theta and phi. This problem looks simpler, appears simpler when we use, instead of Cartesian coordinate, we can use a polar coordinate. I can write using Cartesian coordinate equation of a sphere, that is x square plus y square plus z square is equal to a square, where a is the radius of the sphere, a is the radius, where a is the radius of the sphere, and r is the position vector of a particle relative to center of sphere, center of sphere, where coordinate system is fixed. Coordinate system is fixed. Now, theta is the angle here, P of xy. Okay, this is r. As in case of circular motion, similar, instead of circle we have taken a sphere. Fine. So this is equation. I can write this as using distance formula. Say here r square is equal to a square, or r is equal to a, or r minus a is equal to 0. Now, to describe the motion of a body or a particle moving on the surface of a spherical body or a surface of a sphere. Now, the constraint here is that body which is moving on the surface of the sphere must be in contact with the surface of the sphere. That's one. And to describe its motion, we need three coordinates here. Writing the equation of constraint here. What is the constraint here? The body is moving on the surface of a sphere, and it is at a certain distance from the center of, say, coordinate system, that is r. Now here, if in case of a body, this r is equal to a, if the radius of the sphere becomes equal to the position vector of a particle at a given instant of time, then we can write this equation. This is the equation of the sphere. Well, and then we can write this, or we can write this. This means here the constraint eliminates one coordinate out of three, that is r, theta and phi. Hope you got this. Eliminates one coordinate out of three. So we can have remaining two coordinates, q1 is equal to theta and q2 is equal to phi. q1 is equal to theta, q2 is equal to phi. You may ask a question here. We have written this equation of constraint, and writing the equation of constraint is our job here. That is knowing the holonomic constraint. Holonomic constraints are the constraints which can be expressed in the form of an equation. We have written for the equation for the constraint, and this equation itself eliminates one of the coordinates, that is here r. R is eliminated. In Cartesian coordinates we need three coordinates here. In polar coordinates also we need three coordinates with adequate advantage. Here with adequate advantage, instead of taking Cartesian coordinate, I am taking here spherical coordinates or polar coordinates here, r, theta and phi. Fine. So out of these three coordinates, one is eliminated by, not by you or me, eliminated by the equation of constraint. Constraint reduces the number of dependent coordinates. Out of three, one coordinate is dependent here, which is removed by the equation, which is removed by the constraint itself. Remaining independent coordinates are q1 is equal to theta, q2 is equal to phi. And when we define what is called as a degrees of freedom, there we said it is a minimum independent variables or coordinates required to describe motion of a body. The minimum coordinates or variables here and called as degrees of freedom. So the number of coordinates required here are 2. That means q1 and q2 we are writing theta and phi. So the number of coordinates required are 2, and this is happens to be the degrees of freedom. For a particle moving on the surface of a sphere, to describe its motion, after eliminating a constraint. What is the constraint here? The particle is allowed to move on the surface of a sphere. That means the particle is in contact with the surface of the sphere, and it is at certain distance. Assume that it is at a distance r, which is equal to the radius a. R is the position vector here. R is the position vector from the center of coordinate system, which locates the position of this particle. This coordinate itself we have removed from set of coordinates, and the remaining, which is a dependent, remaining coordinates theta and phi. Only 2 coordinates are enough here. The system called as constraints eliminates the dependent variables, and remaining independent variables are also known as degrees of freedom. Using theta and phi, I can define or say about the configuration of a given system. Here, the 2 coordinates theta and phi are enough to describe the motion of a body. Here in this case, a particle is moving on the circumference of a circle. This is the second example. Let us go for a third example. And the third example here is the simple pendulum. Simple pendulum. Many times we have discussed this. In the first class only we have taken this example. This is the simplest example to tell about the constraint. Let me draw a figure here. So this is xy plane. This is x, so this is y, and we are asking this bob of the pendulum or point mass of the pendulum, say m, to move in a vertical xy plane. So theta is its angle with the vertical axis and L is its length. Now, this is a system called a simple pendulum. We are looking at this example, how it can be a holonomic constraint. The question is, can we write the equation of a constraint? Yes. And what is the constraint? What is the constraint here in case of simple pendulum? Here we have assumed that this simple pendulum, right, of mass m is moving freely, say in a xy plane, vertical xy plane here. O is the point of suspension, m is its mass, and this is its length. We call it a string or the length of the pendulum. Here in this example, see what is the constraint? This mass m, point mass or a mass attached to the other end, called as bob of simple pendulum, point mass, right? And this mass is not free to move. Its motion is restricted. Its motion is constrained motion. What is the constraint here? Say the length of this mass from the point of suspension is always constant at all time. Length of the point mass is constant at all times from the point of suspension. So here, to describe the motion, we have taken x and y, the two coordinates. Now, theta describes the position here. Instead of, I can write this as x square plus y square is equal to L square. Fine. We can write thus x square plus y square is equal to L square, or else I can write this as r square is equal to L square, or we can write r is equal to L. Now, using plane polar coordinate, here, we have written this, of course, using Cartesian coordinate, using plane polar coordinate, that is r and theta. Only two coordinates required. In earlier case, we had r, theta, and phi. Here, r and theta. See, this coordinate is eliminated here. This is the constraint. We have written the equation for a constraint, that is length of the point mass from the point of suspension is constant, and this remains constant throughout its motion. This has been eliminated. Using the equation of constraint. What is remaining here is theta, and this is the angular displacement here, angular displacement theta. Theta is the only coordinate we require to write or simplify the given problem here. So theta is only one coordinate is enough to describe the motion of bob of the simple pendulum. Here I can write theta is equal to q1. Look, out of these two coordinates r and theta in polar coordinates, we select here in some of the cases polar coordinates because after simplification this equation appears to be simpler. Out of these polar coordinates r and theta, so r has been, or r is constant because of the constraint, or as good as we say r has been eliminated. Out of 2, r has been eliminated by not you and me, eliminated by the constraint imposed on this. What is the constraint here? Look, this is the constraint, that is L, the length of the pendulum is constant because r becomes equal to L here using this. So r is constant. R minus L is equal to 0. You can write as like in earlier case, r is been eliminated. What is remaining? This is dependent coordinate, and which is eliminated. What is remaining is independent coordinate. Q1 is equal to theta, and this happens to be a degree of freedom. For a simple pendulum, degree of freedom is equal to 1. Degree of freedom is equal to 1. Q1 is equal to theta. So look at the example number 1, example number 2, example number 3. Say, what we have done is we have taken the problem, we have written the constraint equation, and in all the cases, example 1, 2, 3, we have written the constraint equations, and from the constraint equation we have eliminated 1 or 2 coordinates which happens to be dependent coordinates, and we are left with independent coordinates, and here the independent coordinates becomes equal to the degrees of freedom. Let us take another example, that is example of rigid body. Example number 4, that is rigid body. At the beginning only, it is holonomic constraint. Holonomic constraint 1. At the beginning only, I had told this is an example which happens to be example of constrained motion, and we know about rigid body. It's a solid body. And in case of rigid body here, distance between any two particles is always constant. It doesn't vary with time. That means if you have any body and say this is a rigid body, the rigid body contains n number of particles here. It's made up of large number of particles, you can say, and say this is I particle and say this is Z particle. Out of n particles, I and Z, say the distance between two I particle and say Z particle is always constant, and that is a constraint here. We write this as a constraint. We have to write the equation for this constraint. In case of this rigid body, if I write that say RR modulus of RI minus RJ is equal to a constant CIJ, the distance. we can write this is equal to constant. Fine. This is equal to constant. That means distance between from the point of suspension or from where Ri. What is that R? R is the position vector of that particle. So this is understood. Say if I fix a coordinate system here on this body, this is origin, and say this is Ri particle, and say this is J particle. So the distance between I particle here and J particle from the origin here, that is Ri. I is the position vector here and J is the position. This distance is constant. And we have written this as Cij is constant. It doesn't vary with time for a rigid body, perfectly rigid body. A rigid body is the one which cannot have a deformation. That means it cannot change its shape under the action of external or internal forces. So, deformation, if there is a deformation, if there is a contraction, what we call, that contraction is very, very small, so we can neglect it, and this is how we call a body as a rigid body, in which all the time the distance between any two particles is constant. And we have written this as an equation. This is a constraint. This is the constraint. Now we can write this constraint in terms of using popular coordinate system called as Cartesian coordinate system. Let me write this as in terms of coordinates. If say xi, yi, say zi are the coordinates for ith particle, and say xj, yj, zj are the coordinates for the jth particle. There are number of particles. We have taken only two, r, that is ith and jth particle. So for a ith particle, these are the coordinates. For the jth particle, these are the coordinates. We can write using this the equation for a Cartesian. Using Cartesian coordinate, we can write the equation for a rigid body. Say for example, xi minus xj square plus yi minus yj square plus zi minus zj square, which is equal to Cij square. Once we write this, we can say here, a very important point to be noted, the constraint here. The constraint is distance between any two particles is always constant, and it doesn't vary with time. We know it doesn't vary with